All right, let's talk about one of my favorite data structures, the trie, also known as the prefix tree. It can be a really great structure for lookups of certain types of data, and we'll see a little bit more about what that data has to look like for it to be a useful data structure. So we'll talk overall about the data structure. We'll look at an example of using it as a string map, for example, to see counts or indexes of different strings, or we could also use it for things like looking up dictionary definitions of strings. The trie, as I said, is also known as a prefix tree or prefix search tree. It's a specialized tree that has up to m children per node. So it's not a binary tree like we've often looked at. It's an m-ary tree where m is the size of the alphabet that might be used here. So for standard words, it might be 26 children for each node, each letter of the alphabet. Another thing that tries can be very useful for is DNA, genetic information, where we'll have only 4 possible values in the alphabet, and therefore only 4 children per node. So that could limit the scope of the tree and be a little smaller, fit a little better. It can be very applicable to your data if the keys that are being used for lookup can be decomposed into a sequence of subkeys, like how a word can be broken down into each letter in that word. You might deal with the first 1 letter, first 3 letters, first 7 letters, etc., all the way out to the length of your full word. So speaking in more generic terms, if we have a key k, then we treat that key as being composed of k sub 1, k sub 2, k sub 3, and so on out to k sub d, where k sub d is the length of the key. If we know the maximum length of the longest key we're going to look up, that can be really helpful, as we'll see in a moment. We also need it, however, to have some redundancy between those subkeys, meaning there should be some overlap in the contents of those keys, such as words that start with the same few letters. It's usually best if it's the starting values of our keys in particular. Like many words start with the sequence THE. The word the does, the word there, the word them, and so on. This helps us in our trie being useful for the kind of data that we're dealing with. It's most commonly used for strings, such as words, binary sequences. As I said, genetic sequences of DNA can also be a useful thing to use a trie for. It's interesting to note that the key you would be looking for is not actually stored in full anywhere in the tree. It's implied by the structure of the tree. So if we were looking up the word the, we would not store the full word the anywhere. We would store a node that represents T being a first letter and another node that represents H being a second letter, therefore a child of T, and another node that represents the E. The real values that we'll look up will only be stored at nodes with complete keys. And as we'll see in a moment, those nodes will not just be the leaf nodes. So if we want a bit of code to represent a node in our trie, a very simple way to do that is to create an array for children that will have up to your alphabet size of space in it, so that each item in your alphabet could have a slot there. If every starting letter exists, for example, A through Z, there are words that start with all of those letters, then our root should have children for all of those letters potentially. In smarter designs, we could reduce this down to only the values that are actually used in the keys we're representing. But for our purposes, it's pretty simple to just create an array with, for example, for words, 26 slots for children. We have a Boolean to indicate whether this node represents the end of some key. Because as I said, it won't just be leaf nodes that store our values. And then we'll have a spot for the value that will only be used when the node that we're at represents the end of a key. So let's look at a real example here, using the rhyme, "She sells seashells by the seashore." We've got some values to associate with those, which should be the sequence of the last time that word appears in our rhyme. She is the first word, sells is the second word, and C appears several times, so the last time it appears is at index 6. So we've got some values, that's really all that matters, and these words can be stored in a trie. If you look at the words, for first letters, there are only 3, B, S for many of the words, and T for the word the. So our root represents no keys at all. It could represent the empty string if we ever needed to store information about the empty string, but otherwise we need just one empty root so that the first level of nodes represents the first letter of possible words in our map here of words. So we see B, S, and T all have nodes at that first level. Under B, there's only Y, because the only word that starts with B is by, and that has index 4. So at the node for Y, 4 gets stored, so that we could look up that key of by and find that its value was 4. Most of the values are stored at leaf nodes in our example here, but in many tries that will not be the case. And here we can see that one key, the word she, ends at a non-leaf node because it also is contained in the word shells. So if we went to look up the word she, we would look at S, we would look at the node for H, we would look at the node for E, and we would be able to see that its index is 0. But if we were looking for the word shell, we would follow the same starting path, and then we would keep going until we finish that word through the L's and so on. So this stores all of the words that we had there with all of their values, and you can see that it doesn't need to create full entries for every word. In fact, none of the words are actually stored fully. They're stored letter by letter as sequences in building up the keys. Let's dig into a closer look at just some of the values there. We can see this trie represents she and sells and C, S-E-A. What this one also represents is the empty spots for the 26 possible values for the alphabet, and that the characters in a word are only defined by their links to each other as you go from parent to child to child. And then each node has an array of these links for possible next children nodes, and they have a spot for a value, but the values are only stored at the nodes that represent the end of a key. So we have that map of strings that we've looked at as an example. The string decomposes into a sequence of letters, and so each of those letters is treated as a subkey, and every trinode other than the root therefore represents a letter, represents some subkey. Every level of depth that we step through adds another character to our key, so we can build up longer and longer words. This means that our space will be O of m times n, where m is the size of the alphabet, 26 for example in the case of words, and n is the total number of strings. So I might end up having to create for every string 26 spots for each of its letters if there were not very good overlap between them. When there is very good overlap, we'll be a little smaller than that m times n, but we'll think worst case. The worst case is we have to, for every word, create that set of 26 children for every letter in it, and so on. So the space that it requires will be O of m times n. The time to find, insert, or erase things inside of that trie would be O of d times m, where d is the length of keys and we want to think about the worst case, which would be the longest key that we have. Even in the case of a dictionary of all known English words, there is a maximum length to the longest word in there. And so we still know a bound on how far down you would have to step, letter to letter to letter to letter, to look up the definition of whatever is the longest word in our dictionary, for example. Because each of those, D and M, are constants, we could look at what the number of letters in our alphabet is, or the number of characters in our alphabet is, and we could look at the length of the longest key that we might get. Then we can treat both of those as constants, meaning, in big O terms, they both boil away. So our space of O of M times N, it's functionally O of N space. And our time of D times M, both of those are constants, therefore it's functionally O of 1 to look things up. If you give me a word that's 20 characters long, it will take me only 20 steps to look it up. It will not take anything related to the number of strings stored in that trie to be able to look up your particular key, or to insert that key, or to erase that key. So the properties of the trie are we get really predictable operation time if we know the length of the longest possible key that we're going to store. We know the maximum lookup that will be required down to the number of characters in that longest length key. So it's based on this D, the length of keys, not N. Doesn't matter how many strings you store in that trie. So if we stored all of the 5-character sequences of letters, that would be 26 to the 5th possibilities, meaning 11 million words. In the case of our trie, it would take only 5 operations to traverse the trie for any of those keys, any one you want to look up or erase or whatever. It would take only 5 operations. Whereas for a hash, to do a hash table, for example, yes, it would take 5 operations to calculate a hash function probably, to combine the letters of that word somehow mathematically and find a nice hash, but we also do need a good hash for the hash table, and we'll see some complications to that. In a BST, the lookups are log n, which means that it's actually possibly about 24 operations to traverse through the BST to find things in there if we had to store these 11 million words, versus the only 5 operations to look something up in the trie. It works best with shorter keys, as in we don't want that D, that length of maximum key, to be extremely long, and it especially works well when the subkeys are clustered in some way, meaning that we have those nice prefixes like the she and the shells where they overlap, and we don't get a bunch of branching in it. But even if we do get branching, unlike the BST, we'll still have quick lookups in terms of the operations, looking character by character. It will take more space in the trie if our subkeys are not clustered well. It allows us to do ordered access, finding the minimum, the maximum, ranges of things, successors. I'll show you an example of that in a moment. It's particularly good for prefix-related queries, like doing autocomplete on a phone or when someone's typing. If you typed the SH, you would be able to look at all of the keys in that subtree under SH and find that she or shells are 2 possible valid completions of that key. So let's use the min as an example of another way that the trie can be very helpful. So if we look back at the bigger trie that we did here, to find the minimum valued word, the earliest alphabetical word in here, all we have to do is start from the root and look at its children and find the child with the earliest alphabetical value, B. And then from there, we repeat that process. We look at all of its children and we find the child with the earliest alphabetical value, which in this case there's only 1, so it would be the word by. But if the word B, B-E, was in there as well, then we would choose the E because it's an earlier alphabetical value, and we would have the earliest key that way. So we can find minimums, we can find maximums by repeating the same process. T is the highest value, then we look at the highest value child under that and highest value child under that. So we can find mins and max, for example, very easily and very quickly inside of a trie too. So the other thing that a trie has a benefit of is, unlike a hash table, which we saw has a quick speed to calculate hash functions, we don't have to worry about finding a good hash function. You may recall, if you've seen hash tables before, and we may talk about them more later, that if, for example, your hash function always returned the same thing for every key, then you end up with an array, and you end up with the same bad behavior as we've seen in dealing with just flat arrays. And we don't have to do any collision resolution. In fact, we want collision. We want things that overlap in part, at least, like the THE in the, mapping also to them and there. So here's an exercise for a few more keys that are a little longer than the ones we looked at before. If we needed to build a trie for these following strings, then we actually can build the trie word by word, where, for example, if we saw the word bear, then we could build it by having the root, starting a node for B, then building underneath that a node for E, and underneath that a node for A, and underneath that a node for R. And that would build part of our trie out for us. As we saw Bell, we would see we didn't need to build the B or the E. We would just build nodes for L and L underneath that. Now we have two words represented. Similarly, bid gives us the I and the D under B. And we just build these new subtrees as we need to for nodes that don't already have a representation in our trie there. So with a trie, we get efficient storage for things like maps with string-based keys, genetic data, binary sequences that might have repetition in them, and anything else that we can break up into these sorts of prefixes. It's especially efficient when the trees share common prefixes, gives us O of n storage with that modification of how big our alphabet is, and it gives us O of 1 operations. The length of the longest key is all we need to know, and then we get that O of 1 behavior. And we get some efficient operations like finding the successor, the range, what the largest and smallest sort of things are, and doing neat functions like autocompletes. We will use the trie for a particular algorithm that we'll study later called Huffman coding that allows us to compress down large amounts of data without losing any information. So look forward to seeing that with you.